Hello everybody, welcome to my presentation. In my research, I am going to propose a connected vehicle-based cooperative adaptive cruise control algorithm to divide and reform a connected vehicle platoon at signalized intersections. First of all, I would like to introduce my basic idea. So there is already a CACC algorithm that works fine in freeway settings. It can maintain a small headway so that traffic throughput can be improved. I would like to adopt the CACC algorithm into urban driving environment where suddenly stop and reforming of a platoon is frequent. So only with the help of connected vehicle technology, a new algorithm can be proposed. So in the new so-called CV-CACC algorithm, there are new two functions. The first function is dividing a CV platoon. The second is reforming a CV platoon. So let's go to the division part of the CV-CACC algorithm. Before we divide a platoon, we need to know where the division point is. So there is a small and simple division point prediction algorithm applied before the main algorithm, like is shown here. So a front portion of the platoon is going to pass the intersection, and the remaining part has to stop. For the remaining part, a virtual leading vehicle trajectory is derived to lead the new platoon to a safe stop, and at the same time, an acceleration dynamic function is added to the benchmark CACC algorithm, replacing the old dynamic function, which is based on speed. So you will see the results later. For the reforming part of the new algorithm, the design is that all the vehicles will connect and share data and decide trajectories before merging. And one vehicle in the original platoon will decelerate and make some room for the new vehicle to merge. So there is a three-stage rule for the vehicle to plan its trajectory, to make some room for the new vehicle, and the result is that eventually the original headway setting is maintained. In the simulation part, we first of all tested the benchmark CACC and found that it failed in our setting because the vehicles would overlap with each other and their trajectories intersect. We changed the headway setting in the benchmark CACC and found that if we set it too small, they will collide into each other. If we set it too big, some of the vehicles will fall apart from the platoon. We also tested our new proposed algorithm. We tested the division part and the reforming part, and we found that this time the trajectories do not overlap with each other, and the speed curves converge, and the acceleration curves also converge. So this is a good sign, indicating that our designs worked well, at least in the simulation environment. So here comes the conclusion and future studies. In this study at the current stage, we proved that our CV-CACC algorithm is capable of dealing with sharp breaks and abrupt merging requests in connected vehicle urban driving environment, and our next stage is adding more quantitative measure of effectiveness for this research. Thank you for listening.